Mic check. Mic check. Hi, everyone. So get drinks and food on napkins. We don't have paper plates, and just bring them to your seat. You can eat and drink, and you can get up and walk around. If you don't know this already, the bathrooms are just down the hall. You walk out and to the left. If you need to get on Wi-Fi, the password and the ID is over there on that board. If you can't see it and you need to get up to get it, please go ahead and do it. This is I have to say, this is a special event, different from what Disruptive Technologists usually does. This is a student capstone project, and it's about robotics, accessibility robotics. And as you can see, we have tons of speakers, and you can see we've got some very cool robots. If you look to the far left, there's a little one there that looks like a little person, and it actually walks up steps. And if it disappears, it's because it's going to be in my backpack sneaking out the door with me later. I want to thank a lot of people, but first I want to say the team that put this together was an incredible team by adjunct professor Jabril Benestrin, and they are Steve Galezi. Oh no, wait, that's one of the speakers. Sorry. Let me just do this really quick. Angela, and Bowen, and Jaswan, and Jincheng, and Jessica, Mahitha, Pani, Srivansan, Ziopin, and Zioyang. And I just want to say that was the best. I hate to say this for all my old capstone students, but this was the best group I've ever had. And I've already been asked by several of them to join the team. So as of tomorrow, I've already selected a few to be on our Disruptive Technologists team going forward. And we're an all volunteer organization, and we help minorities, women, and disabled, and people of all backgrounds to become disruptive technologists. And accessibility is one of the things that we do for people, help them learn how to become more accessible and equal with other people. Anyway, Jabril, I want you to raise your hand. This is our mentor. He's our guide, and he puts these amazing groups of people together. I also want to thank our sponsors. We actually have one of our sponsors, well, actually two. Jabril's a sponsor, but also Esther Dyson is one of our sponsors. She's also on our board of directors. Esther, thank you. And Ramona Wright, and NYU, and UC Berkeley. We actually have some UC Berkeley t-shirts to give away. I know this is NYU, but they're one of my sponsors too. And we have, it's hard for me to pronounce the name, but it's Koznak Bowen. Where are you? What's the name of the Kozrak? And tell us a little bit about Kozrak, our new sponsor. Oh. Okay. Great, great, thanks. Jeff Ziotag, Jeff Paul is also a sponsor, and he's also our videographer, and he handles all of our video, and it's actually pretty incredible because he actually puts together a table of contents. So when you watch our video, you can actually flip to the one you want to listen to. If you don't want to listen to any of the speakers except for, let's say, one of them, like Sage, then you can just skip everyone else and just go to Sage. It's a very cool app. Yes. Very soon. And Also, Jim Williams is on our board of directors. He's our treasurer. And we have a friend visiting from California, Glenn. Say hi. He's actually made a few creative things himself. You made a few robots too, right? Lots. He's a toy maker. Anyway, we're gonna go with that. We've got a lot of people here. They only have a few minutes. Everyone has 5 to 10 minutes to kind of present or talk about and show what they want to demonstrate. So they each have like their own 5 to 10 minutes. They have 5 minutes. I know it's really short, and I know that our first one has a team of 6. 6 people, Farouk, and he might need 10 minutes, but you are totally, this is an NYU college student, totally fun, interactive event. You can ask questions. The speakers and panelists, you guys can ask each other questions. You can talk about, show what you want to do, but everyone can talk. Just raise your hand and I'll just point to you and you can talk. This is not your normal event. This is just fun. And like I said, get up, eat, walk around, go to the bathroom, whatever. Anyway, we're about to start. And then at the very end, which will be in an hour and a half, we're going to give away, a lot of you put your names in a bag, and I'm going to pick them out. We've got some Cal t-shirts and some different books to give away. So anyway, let's begin. Farouk, since you've got the biggest team, I want you to start. Go for it.
Hi, everyone. I'm Farouk Zia, and I would like to make a short presentation. So I guess we are going to need some help from, if you don't mind. So I didn't bring my laptop, and I'm sorry. Could you please tell us your name? I know it will be your turn in a few minutes, but McKenna, thank you. Yeah, McKenna agreed to help us a little bit because we were trying to figure out which laptop works with the projector.
Right. Good evening, everyone. My name is Josephine.
My name is Jay Patel.
I'm Neil.
And I'm Frank Lee.
And we'll be discussing about our the VIP team, Smart Wearable BioTracker VIP, which we will discuss about what we do. We will go over what the team does, some theoretical background, some hardware prototypes we have done, some published works the team has done so far, and also we'll wrap up the presentation with a conclusion.
So our objective is to build an AI-enabled device that can help people with disabilities or with some diseases like Parkinson's disease. And the motivation for us to do this kind of project or having this kind of object is that we have the data. Like each year in the United States, there are over like 90,000 people who are diagnosed with Parkinson's disease, and also there are over 700,000 people who experience stroke each year in the United States. So we are hoping we can have a kind of device like this to help them to have a better living standard. Our device is kind of used to predict their gestures, predict what they are going to do with their hands or gestures. So yeah, that is our objectives. And for some applications, while we are developing, we found some possible fields that we can use for our device. Like for the medical use, we are thinking to use our like gesture predictions to drive this kind of prosthetics or other devices that can help them to like perform the hand like performing like a hand. And also we are thinking to use them in the augmented or virtual realities that can help our users to immerse better into the virtual world instead of using the controllers, which is still a little bit weird right now. But if we can have this kind of device to predict the gestures, maybe we can like only use our hand and thus to immerse better.
So surface electromyography is a technique used to measure electrical activity produced by muscles when they contract. So it uses sensors placed on the skin above the muscles to detect these signals. Some pros are that it's very specific in detecting which muscles are active, and it's widely used and supported by a lot of research. Some cons are that it can be sensitive to other electrical interferences, and it requires like a lot of prep. So like to clean the skin, and this can get kind of messy. So mechanical myography is a technique used to study muscle function by detecting the vibrations or sounds the muscle produces when they contract. This is done by using sensors such as accelerometers or microphones placed on the skin over the muscles. So some pros are that it's useful in environments where electrical signals are problematic, and it can offer additional information about muscle mechanics that isn't available through electrical signal analysis. Some cons are that it's sensitive to external movements and ambient noise, which can interfere with accuracy in measurements. And finally, force myography is a method used to measure muscle activity by detecting the pressure exerted by muscles on the skin surface as they contract. This is accomplished by using pressure sensors that are typically placed in a band around the limb. Some pros are that it's quick and easy to set up without any need for skin preparation or conductive gels. And it's less sensitive to electrical interferences, which can be beneficial. Some cons are that it might provide less specific information about which individual muscles are contracting compared to the other two.
All right, so now for deep learning, just to give you a brief overview of what deep learning is that it's a subsection within machine learning. And in particular, it has a more black box methodology in the sense that in machine learning, we have to do far more feature engineering, where we have to tell the program saying that I'm looking for this, this, and this feature, whereas in machine learning, we can give a large sum of data and it's able to extract those features. Well, there is, of course, a trade-off when it comes to this, in the sense that deep learning models are far more data hungry and they require more parameters due to this extensive feature. But the trade-off is that it's able to pick up on these finer details. So a couple of deep learning models that and architectures that we looked into when forming our models was MLP. MLPs are very basic. They're used for linear regression and classification, pretty straightforward methods. And the next one was convolutional neural network, also known as CNN, but they excel in image processing and videos. So as if you were to think about a human understanding a image or a video and understanding the graphs. Another part of deep learning architecture that we took into consideration were LSTM, also known as long short-term memory networks, which helps enhance RNNs by learning order dependencies and also helping with the prediction problem or preventing long-term dependency issues. And finally, transformer models. And I think we have all heard of ChatGPT. It's a form of transformer model that ChatGPT and BERT and T5 all are used for, let's say, natural language or for text. But these same methods for transformers could be used for signal processing in an effort to understand the context and predict the future. Next step within deep learning and in our project was gesture recognition. As we talked about previously about surface electromyography and mechanical myography and force myography, these are all biosignals which are used and can be used by machine learning methods and deep learning methods to interpret and understand what our future hand gesture may be or predict what will be next.
So we'll go over some hardware prototypes. So I'll briefly explain this one. This is some of our old prototypes that we have done by our former members. I'll further explain within the design itself. There are 4 sensor units and there is one main unit that has a microcontroller. Within the 4 sensor units, which I'll explain further into the next slides, they consist of a pair of accelerometers inside. We're going with the mechanomyography method, muscle detection, mainly because we do want to come back regarding with the drawbacks of the SEMG, which may relate to in cases of, for example, in your smartwatches, it's very sensitive to temperature and also regarding with sweat. So regarding with the bio signals, the values do change. So we wanted to come back regarding with this. So we stick with the mechanomyography muscle detection. And the reason we didn't really go deep in detail with this is mostly because we wanted to make the design much more professional. We wanted to use better 3D mechanical shell resin. So we have our first prototype here. It's very similar, as you can tell, to the first prototypes that you have saw earlier. It uses the resin. It uses a tough 2000 resin, mostly because of its blueness. And the accelerometer that we use is 80XL345, mostly because there is a wide variety in use of SPI connections and also I2C. We wanted to send the data as much as fast as possible. So that's why we stick with this one. And we connected in SPI configuration. And within each sensor unit, as I explained, that there are 4 sensor units and there's one main unit. There is a noise accelerometer and there's a skin. The skin accelerometer is mostly towards closest to your arm. So whenever you do a certain gesture, the rods will move up and you see the units will change. These accelerometer units are within our G units, so gravitational force. These are calibrated later within -2 to 2G, mainly because the frequency regarding our muscles is very less, maybe like around less than 50. So we kept it around in that range. And for the noise, this is just there mainly in order to get pure muscle readings, we wanted to subtract skin and noise so that we have an actual just muscle readings. And we also do have another prototype, and you're wondering why make another prototype. Well, regarding with this one, the performance, we did data collection with this one with 21 subjects, and there is approximately at least 90% accuracy in gesture recognition. But we wanted to compare that to another prototype which we created here. This is our second prototype, and you're wondering what's the difference between the two? Well, the difference between the two is the number of bits, data bits. The first one, the 80XL345 has 10 bits. This one has approximately 16 bits. So from the number of bits, we assume that if there's more bits, it's going to be more sensitive. So in a case where you bump against something, it would pick that up as well. So this is why we went with a smaller accelerometer. Everything is sort of shrinked down. However, it still has the main unit and the 4 sensor units. And regarding with the workings of this, we still haven't done data collection, but we do plan to compare the first prototype and the second one to see if the gesture recognition is approximately the same or if not better.
So we got some exciting work that we have published. The first one being regarding, the title is Hand Gesture Recognition via Transient Phase. And if you're wondering what transient phase is that when you're creating a hand gesture, let's say you're making a fist, from rest to that fist phase, that initial jolt of electrodes that are passed through your muscles is part of that transient phase. So we thought, why are we predicting or recognizing a hand gesture when the signal is already sent? We should make a prediction when that first jolt is coming through from your brain to your hand. Therefore, we created a model using efficient CapsNet as a deep learning model that would allow subjects to predict their hand gesture using only 5% of data. So initially, we started off with only 5% of the data, achieving a 70% accuracy, and we pushed it to 20%, achieving 80% accuracy. The main reason why this is very important is because this model is able to be generalized for all of us. We all present a different senses and different sensors when we're making a fist. What we did was we created a generalized model which can be applied to each one of you, and then it could be customized to each subject. The second paper was regarding channel dropout. So as sensors get old and they degrade, there might be a time when they lose a connection or they stop sending signals back. This is a common problem in modern hand wearable technologies. So to combat that, we created a model that even if we removed, let's say 25, 50, 75% of the channels, it would still be able to accurately predict what hand gesture will be coming next. This talks about the robustness of a sensor or of a device so that the longevity of a device can remain.
Okay, so now we have prototype 1 and 2, and in the future, we are thinking to add FMG, the force myography, to our device to whether to use this as a like a support to the MMG signal we have, or in some other ways, do they cooperate? We are still working on researching that multi-modality myography right now. And also we are still trying to build a FMG signal receiving like sensor right now. We are thinking to use the 4 sensory resistors to detect the FMG signal. And also we are kind of thinking into how to place those sensors in our arms to make a better like FMG signal recognition and how to use that signal with the MMG signal.
And finally, as we would like to, in the future, see our product out in market, it is also important to make this user-friendly. In particular, when we're putting on sensors on ourselves as a wearable technology, a few millimeters off could completely throw off the accuracy. As a result, by working towards a model that even if it's off 5 millimeters from its original location, it should still preserve its accuracy. So that's why we're working on how to do optimal patch encoding and how to also do flexor and extensor predictions. Thank you guys so much. Appreciate it.
Thank you. Thank you, everyone. Thank you for those who waited till the bitter end here. I really appreciate it. We went a little bit over because we started a little bit late, but you guys did a great job. What's going to happen is I'm just going to pull some names out of a hat. We've got 5 UC Berkeley, New York t-shirts. 4 of them are women's, 1 men's, and we've got 5 books that are on pretty cool, innovative stuff. So I'm going to call your name, and Andrew, wave your hand. And if you could put the stuff on chairs and just come and grab whatever, if you want it. And if you're a guy and you want a t-shirt for your girlfriend, grab that. Okay, so Neil Kumar, Theo Chivu, Jessica Shaw, if any of you are still here, Anish, Pan, Lisa Palmer, Angelo, and Jay Patel. And if you don't see anything you want, totally understand. Let's see, I think that's 10. Oh, wait, I can add a couple more. Ansma Patengar. And Siddharth Barthai. I pronounce names terribly, but thank you everyone for coming, and I hope you come to our next one. We're going to probably do more of these. Thank you, NYU Capstone team. You guys did a great job. I would love that. And you have my card, right? Yeah. You already got it? Okay. But I would love that. God, if you could share that, send that to me. We're gonna post it on our YouTube channel. Hey, thanks, Bowen. So, you want to be part of the team?
I'm sorry, what?
So you're gonna be part of ET going forward?
Thank you.
Great.
Yeah, that'd
Love
be
having you.
great. Yeah,
Thanks,
thank you.
thanks for your help.
Excellent today, man. Everything going well. Wow. I truly feel happy for all of us. Yeah.
It was fun and it was very informative. Oh,
Keep it in touch.
there's still. There's still 2 books and a woman's t-shirt. So if anyone wants them, come up and get them. 2 pretty cool, innovative books and 1 woman's large t-shirt.
Thank you very much.
Hi, do you want a book?
I just took it.
Oh, good. It was,
Yeah,
you were
it
great.
was my name.
You know, Angela, let me give you my card. I would
I know
love,
you gave me.
okay,
Yes,
I would
yeah.
love to interview you for our website.
Yeah.
So, why don't you do this, since I don't have too much of your stuff, why don't you email me? My email's on there, or call me or text me, my phone number.
Yeah.
And let's interview next week.
If there is anything on your card.
Yeah,
Okay.
yeah. I'd love to interview you about your thinking.
Yeah,
Sure, it's great talking with you. It's really fun.
Thank you. Thank you.
Congratulations on your.
Thank you.
I have a question actually about for your I know you say you feel like it's a stroke, right?
Yeah.
So my question is that when like for patients that do have that that type of condition, what are your thoughts on, like, do you think that we should be reliant on the technology or rely on the technology to help them, with the stroke? Like, do you think that like, it will be, like, for your body, like, it can help perform, help care?
Sure, because our model is also based on gaming.
Okay.
It would have both in two ways of like solution for of course like the idea is that you have like team goals the doctor they will use always there's always a robot. So it can be a robot at the doctor like studio, or in this case it's better for everyone if they have like a robot like they can practice, they can also exercise. So they are like exercise and exercise.
So you can go beyond therapy.
Yeah. That's also our thought is also to make game eventually online, so that you see your exposure, you see also other American users, of course, so that you are also involved with they go with better if you have someone that you have like. So you have also with better, you have always someone like people competing with you.
Right.
So we are engaged with the game.
Also, it's kind of make that competition thing like that.
Yeah, the competition looks like we'll walk in, wake up in the morning and say, that's the way we did.
Oh, that sounds very cool.
Yeah.
So, and then like, I mean, I'm not, I mean, like, I know you're not doing all of it, but like, but do you think it will be data, like, how to train the actors?
That goes way beyond the talk. First, why not? So after now there is sensor for everything.
Yeah.
Sensor that the bio sensors that can have like people like abilities fully like processing now. So why not? It should be like a sensor that can of course collect data on your set of like your thoughts. You are like if the gaming is your thoughts, you are of course putting in some kind of like like that in the future, but of course the next step is moving forward so that okay, I'm now collecting data on LP users and I see that so yes, it's possible to our solution is feasible. The next step is of course go to what you land on other hospital asking stroke patients to play our game at the city. So it is for all the things that help the user, but it's also stroke patient. We collect data from patients also. We can compare the data with from the stroke patients with the data from the healthy users. We can compare them. We can see what is the difference in the movement, something like that. And maybe later we can also implement what you said. So we can also have something that will not only like the game, the user training mode, but we of course will collect data also on the
Are you like the money check? Are you like the money check or like this? Oh, okay. Like video for like people that have a job, like LinkedIn.
Yeah,
Yes.
sorry.
Yeah.
Yeah.
Oh yeah. So this is make people connect.
Yeah, sure. Actually, I'm not so like active on it, but yeah, you can follow me without any problem. You know, yeah.
Where you from?
Italy. So if you go like your physical interface, better for B2B search for you. You will see by yeah. Yeah, you will see by
So like in Italy, like how far are they like, are they in terms of scope, in terms of scope, is it how in Italy, how far?
it's like a huge there's a huge lab which is the lab where I would like go after my graduation. I will go there and make like 2-3 months of that, and then I'm fixing the come back here and I will that lab is really like one of actually here level. So in biorobotics, biomechanics, education, and education. So when I told them I research here, they were really interested because also they like research now is moving forward. So from this point of view, so how we find cheap solutions and that can be used for whatever other like patients, patients with a disability, so that they can practice at home without going to the doctor, without spending too much money. So they also go in this direction. So yeah, that's a good thing.